We're going to have a look at an example of a Markov model that actually gets used in real life for modeling the spread of infectious diseases. This model is called the SIR model, where the S stands for susceptible, the I stands for infected, and the R stands for recovered. And those are our three states in our Markov model. Now we're going to suppose that you can change state once a week. So that means our timescale is weekly. And we need some probabilities to know from 1 week to the next what state you're likely to be in. So let's have a look. If you're susceptible, we're going to say that it's actually reasonably unlikely that you're going to be infected. So let's give that a 10% probability. And in this model, we're going to say that if you're susceptible, you can't go straight to being recovered. You have to go through being infected, so our probability there is 0. So that leaves us that if you're susceptible, then with a 90% probability, 1 week later you'll still be susceptible, you won't be infected. Now let's have a look and see if it happens that you're infected, what happens 1 week later. Well, if you're infected, then we're going to say that you have a 20% chance of being recovered, but most of the time, that is 80% of the time, you're going to carry on being infected for another week. And notice that you can't go from being infected to being susceptible again, so our probability for that is 0. Finally, let's have a look if you've recovered. What are your options? Well, you can't really go from being recovered to being susceptible in this model, so we're saying you build up full immunity. If you've had the infection, you can't get infected again. So we also have that the probability of going from recovered to infected is 0. So that means if you're recovered, then there's a 100% chance 1 week later that you'll still be recovered. So there we've drawn the transition diagram, and the next thing that we need is we need our transition matrix. So I'm going to put my states as S in the top row, I in the second, and recovered in the third. So my columns follow the same format. So if I put in my probabilities, the probability of going from susceptible to susceptible we know is 0.9. From going from susceptible to infected is 0.1, and from susceptible to recovered is 0. Now if we have a look at infected, we go from infected to susceptible. We can't do that. If you're infected, the probability that you stay infected is 0.8, and the probability that you recover is 0.2. And finally, if we have a look at recovery probabilities, recovering, you can't go back to being susceptible, you can't go back to being infected, all you can do is stay recovered. So there's our transition matrix. So what can we use our transition matrix for? Well, we can use it to tell how, if we have a certain initial population divided between the three states, what they'll look like 1 week later. So if, for example, we have an initial distribution that has 99 people who are susceptible, 1 person who's infected, and no one who's recovered, then the question we might ask is, what is our population 1 week later? So notice that I'm saying that my population initially, i.e. at time 0, is given by V0, and 1 week later is given by B1. Well, our transition matrix is what we can use to do this. So that's the whole reason we set it up the way we do, is we have that V1 is equal to our initial distribution times by our transition matrix. So if we put in some numbers, then we'll have 9910 times by our transition matrix. And if we do this multiplication, then we'll see that we have, so we've got 99 times 0.9 plus 1 times 0 plus 0 times 0. That gives us 89 with a bit of rounding. Then we do 99 times 0.1 plus 1 times 0.8 plus 0 times 0. And that will give us 11 with a little bit of rounding. And then finally for the last entry we have 99 times 0 plus 1 times 0.2 plus 0 times 1, and with rounding that's going to give us 0. So this tells us the population in each state after 1 week. And if we wanted to, we could find the population after 2 weeks by simply having a look at the population after 1 week and multiplying it by our transition matrix. Notice that really what we're doing here when we find the population after 2 weeks is we're taking the initial probability distribution, and since V1 was equal to V0 times A, our population after 2 weeks is given by our initial population times our transition matrix squared. So you can work that out either way, and if you do that, so let's do some working, check that on your own time, then we'll find that the population after 2 weeks is 18.2. And again, there's a bit of rounding happening there. So this is our population after 2 weeks. And it's looking roughly as you would expect. As time goes by, we have fewer and fewer people who are purely susceptible, we have more people who are infected, and we start having some people who've recovered fully. Now, if we were to plot our population over time for quite a few weeks, we'd get something like this. So let's have a look at this a little more closely. So notice that I've plotted here our 3 possible states: susceptible, infected, and recovered in different colors. And you can see that at time 0, we start out with 99 of our people being susceptible, 1 infected, and no people recovered. And then as we calculated at time 1, so after 1 week, we don't have anyone who's recovered yet, but we have some more infected people and fewer people are straight susceptible. And then as you can see, in week 2, we found that we had 2 people who'd recovered, even more people who are infected, and fewer people who are susceptible. So this is looking like a pretty sensible model. And as you would expect, if we look over more time, well, the number of people who are purely susceptible goes right down. The number of people who are infected peaks and then slowly goes down to 0. And finally, the number of people who've recovered increases until when we look 60 weeks after the outbreak of the infection, we have nobody who's susceptible or infected and 100 people who are recovered. And as you can imagine, if we carried on with our calculations, we'd find that nothing changed. So we notice that everyone who is recovered stays recovered, and we don't have anyone in either of the other states. So the question that we might find ourselves asking is, how do you show that your steady state, which we're going to call infinity, so the state that you finally achieve that doesn't change, how do you show that that equals no susceptible, no infected, and 100 recovered? How could we find that number without having to do 60 plus multiplications? We really don't want to have to do that. Well, the key thing to notice about this, that the whole point about being in a steady state is that it doesn't change. So that tells me that if I'm in my steady state and I look 1 week later, so I multiply by my transition matrix, I'm going to end up with my steady state again. Nothing's going to change. So this gives us a handy equation that we can use to work out our steady state. So what we're going to do is we're going to let the steady state that we're looking for be x, y, and z, and hopefully we're going to show that x equals 0, y equals 0, and z equals 100, but that's what we want to show. And now we're going to write out our matrix equation. So we have x, y, and z is equal to x, y, and z times by our transition matrix, which is 0.9, 0.1, 0, 0.8, 0.2, 0, and 1. So now let's do the matrix multiplication there. So that will give us, on the left-hand side, we still have x, y, and z. On the right-hand side, we have x times 0.9 plus y times 0 plus z times 0. So that's our first element. Then for our second element, we have x times 0.1 plus y times 0.8 plus z times 0. And finally, for our third element, we have x times 0, y times 0.2, and z times 1. So we see that we must have 3 equations in 3 unknowns. We have x must equal 0.9x. We have y must equal 0.1x plus 0.8y. And finally, we must have z equal to 0.2y plus z. So let's see what we can do with these. Well, if we have a look at this first one over here, x equal to 0.9x, that tells us that we must have x equal to 0, because there's no other solution to that. And if we plug that into our second equation, where we're putting x equal to 0, we have y is equal to 0.8y, and the only solution there is that y is equal to 0. And then finally, plugging in y equals 0 into our equation for z, we have z equals z. And if you remember from when we were talking about Gauss reduction, this means z, any value of z is true. So we have true for any z. So we almost got our solution. Remember, we wanted to have x equals 0, y equals 0, z equals 100, and we've shown the first 2. But at the moment, we have that z can be any value. But there's one equation that we haven't thought about. One of the key assumptions in a Markov model is the population stays the same. So our population stays constant. And if you remember, initially we had that our initial distribution was equal to 9910, which tells us that our total population is 100. So the thing that we know is that V infinity, which we know is at the moment x, y, and Z must have the condition that the total value, that is the total number of people in each state, must be equal to 100. And this gives us the equation that we can use to solve for the particular Z that we're interested in. So we know that since x equals 0 and y equals 0, we must have that Z is equal to 100, which was what we wanted. So our steady state solution has no people who are susceptible, no people who are infected, and 100 people who are recovered. Sometimes it turns out not to be particularly useful to use a population vector, like the 99, 1, and 0 that we started with. Instead, we use what's called a distribution vector, which shows the proportion of the total population in each state. So, for example, we could express our population of 9910 as 0.99. So 99% of the population are in our susceptible state, 0.01 or 1% of our population are in the infected state initially, and 0 are recovered. And that would be our initial V0. The reason you might want to do this is you might not know the total population, or you might be able to want to have a model that can be applied to many different populations if you know the transition matrix. But we use the distribution vector exactly like we used the population vector in the previous example. So for example, if we want to find V1, so our distribution vector after 1 week, then that's going to be, again, our distribution vector times our transition matrix. So that's going to give us 0.99, 0.01, 0 times our transition matrix. And if you plug that into your calculator, then what you'll find is that you end up with another distribution vector, which will give you that 89% of the population are susceptible, 11% of the population are infected, and none of them have recovered yet. So you get exactly the same information, just in terms of what proportion of the population rather than the exact number. Of course, if I told you that, for example, the population total was 1,000, then you could use that to work out the exact number in each state. There is one thing that our distribution vector gives us, which our population vector didn't, and that's that not only does this tell us that, for example, in this case here, we have 89% of the population are susceptible and 11% are infected, but another way of looking at it would be to say that after 1 week, you have an 89% chance of being in the susceptible group and 11% chance of being infected, and somewhat unusually a 0% chance of being recovered. So when we use a distribution vector, we can also talk about the probability of finding yourself in a particular state after 1 week, 2 weeks, and so on. So that's another reason why you might use distribution vectors rather than population vectors. but the maths works exactly the same. If you're finding the steady state though, remember in the previous example, we used the fact that our population summed to 100. Well, here you know that your distribution has to sum to 1. So we have to have that, for example, 0.99 plus 0.01 plus 0 equals 1. So when we have our steady state as a distribution vector, then what we're going to use is that the proportion in each state added together must equal 1. So you always end up with an equation either that the number of people in each state gives you the total population, or that the proportion in each state sums to 1. And you can find your steady state vector.